On number 7, we're looking at the same type of linear equation. Here again we have a second order linear equation. We have a second derivative term, we have a first derivative term, and then we have a y term. And we have x squared times the second derivative, x to the first times the first derivative, and then just a constant times y. And we want to do the same type of substitution that we did for number 6. And so we'll use the same substitutions. Y equals x to the m, y prime is m x to the m minus 1, and y double prime is m times m minus 1 times x to the m minus 2. That should be a 2. Minus 2. Substitute into the equation so that we get x squared times the second derivative, m times m minus 1, x to the m minus 2, plus x times the first derivative, which is m x to the m minus 1, minus 3 times y, 3x to the m, equals 0. And again, we want to start by combining the x terms together. And when we combine these x terms, they're going to become x to the m. So we'll get an x to the m in each term. We can factor out that x to the m, and that will leave us with m times m minus 1 plus m minus 3 as a factor. And then simplifying inside the brackets, we get m squared minus m, that's by distributing through by the m, and then plus m minus 3. Here the negative m and the positive m will cancel out, so that we get x to the m times m squared minus 3 is equal to 0. I could write that better. And from the factor x to the m equals 0, we're going to get just the trivial solution. So our real solutions come from here. M squared minus 3 equals 0. When we isolate the m squared, we get m squared is equal to 3, and then take the square root of both sides. You get m is equal to plus or minus the square root of 3, and that gives you solutions of x to the square root of 3, and that's one solution, and x to the negative square root of 3. And so our general solution to the equation is y equals c1 x square root of 3 plus c2 x negative square root of 3. And in this case we cannot solve for c1 and c2 because we're not given any initial values or boundary values.